Welcome. In today's lecture, we're going to begin Chapter 19, where we're going to cover the first part of our carbonyl compound sequence and look at aldehydes and ketones. So the good news is that the first quarter or so of Chapter 19 is going to be mostly a review of a bunch of concepts that we've already seen. And we've actually already dealt with aldehydes and ketones in a variety of other chapters that we've looked at. So to begin, let's just introduce them. We have a carbonyl group, which is a carbon-oxygen double bond, consists of a sigma bond and a pi bond. An aldehyde is when we have one R group, or a carbon substituent, flanking one side and a hydrogen flanking the other side. And a ketone, we're going to have two R group, or carbon substituents, flanking the carbonyl group. So our simplest aldehyde is formaldehyde. That's when we have two hydrogens attached to the carbonyl group. And this is used as a preservative. You might be familiar with this from your biology classes if you've done dissections. And the simplest ketone is acetone, which is used as a solvent and also nail polish remover. There are a large variety of natural products that contain these two functional groups. A few that you might be familiar with: vanillin and cinnamon come from vanillin and cinnamaldehyde. Carvone, spearmint flavor, and benzaldehyde, almond flavor. These functional groups are also present in most steroids. So just like we begin every single functional group sequence, we're going to start with naming. We're going to go through our naming procedure similar to alkanes and alcohols, etc. We begin by naming the parent chain, then we identify and name the substituents, then we assign our numbers and assemble them alphabetically. So for example, we have butane, and if we have an aldehyde on our butane, that would be butanol. So we're replacing the E ending with an AL, and we're going to include the aldehyde in the parent chain. So it's the longest linear chain that also includes the aldehyde in our parent chain. Next, we're going to number the longest chain, and we're going to want to put the substituent, the aldehyde substituent, in the lowest possible numbering position. So for example, the correct way would be to put the aldehyde as position 1 instead of position 7. And then at this point, we're going to go ahead and number and label all the other substituents. For ketones, instead of an Al, we will use an one. So this will be butanone versus butane. The parent chain for the ketone must include the carbon-oxygen double bond, and we will also be giving the carbon-oxygen double bond the lowest priority. A couple other criteria that are specific to these compounds and naming. If we have a chiral center in the molecule, we're going to name that at the beginning, and this is similar to our normal convention for naming chiral compounds. And if we have an aldehyde that's directly adjacent to a ring, then this will be a carbaldehyde. So this is a completely different kind of common name for this functional group. We also have a few other common names for specific reagents. These are three that you should be familiar with and memorize. Formaldehyde, the simplest aldehyde, and then if we extend formaldehyde by one methyl group, we obtain acetaldehyde. And if we extend formaldehyde by one benzene ring, then we have benzaldehyde. Benzaldehyde is a very common reagent that's very useful, as it is a building block that contains both a benzene ring, and then we can do our benzylic position chemistry on this aldehyde. So next we're going to go through a series of reactions that you've seen before. These are all reviewed reactions, but these are going to be the reactions that we can use to prepare aldehydes. And the first reaction that we can look at is one from chapter 12, where we were able to prepare a aldehyde from the oxidation of a primary alcohol. We looked at a variety of different conditions that we can use this, notably the PCC or DMP or the Swern oxidation conditions will oxidize the alcohol up to the aldehyde and it will stop there. Remember, some oxidants go all the way up to the carboxylic acid. So these three sets of reagents specifically will stop at the aldehyde. We can also synthesize an aldehyde from ozonolysis reaction. So if we have an alkene that is disubstituted alkene with R groups on either side, then ozonolysis will yield two aldehydes. And we've also looked at an alkyne undergoing hydroboration. This would be anti-Markovnikov addition of water across the alkyne, and that actually ends up in an enol, and then the enol can tautomerize to the aldehyde. And so we actually looked at this reaction not only in lecture, but we also had a lab earlier in this semester where we looked specifically at this tautomerization, and we did this lab in person. And for the preparation of a ketone, if we have a secondary alcohol, we're never going to be able to obtain the aldehyde from the oxidation because we have these two R groups present, but oxidation of a secondary alcohol will result in the ketone, and we can even use the stronger oxidants here because we can't oxidize further than the ketone. Ozonolysis of a tetrasubstituted or trisubstituted alkene will give ketone. A trisubstituted would give a ketone and an aldehyde as the product, but a tetrasubstituted alkene will result in two different ketones, unless this is a symmetrical alkene, but it will cleave to form two ketones. And instead of getting the anti-Markovnikov addition of water, we could do the acid-catalyzed hydration in the presence of mercury, and this will result in the Markovnikov addition of water across the pi bonds, which will actually result in an alcohol, but the alcohol will tautomerize to form the methyl ketone. And the final reaction that we have looked at is the Friedel-Crafts acylation. We looked at this last chapter where we're able to take a benzene ring and generate a ketone from aluminum trichloride and an acid, an acyl halide. So the next thing we're going to look at is the reactivity of the carbonyl group specifically, but also the reactivity of all of these different carbonyl groups that we will see over the next couple of chapters. So just to talk general about the carbonyl group first, we have a carbon-oxygen double bond. Now there's a large amount of electronegativity difference between the oxygen and the carbon, and there's a resonance structure where we can push all of the electron density from the pi bond up onto the oxygen. And this shows a fully blown positive charge on the carbon and a negative charge on the oxygen. Because of that electronegativity difference, there's also an induction where the oxygen is pulling electron density through the sigma bonding framework up to the oxygen, and that gives us a partial positive charge on the carbon. So this makes the carbonyl carbon extremely electrophilic. And we've seen the electrophilicity of the carbonyl compound in a few reactions already that we've looked at, like the Grignard reagent and the reduction of carbonyl compounds to alcohols with hydride reagents. But in general, we can take most nucleophiles and form a new sigma bond at the carbonyl carbon while breaking a carbon-oxygen pi bond. So we're going to go from an sp2 trigonal planar carbon center to an sp3 tetrahedral, and this is generally going to be an intermediate. Let's compare the electrophilicity of a ketone relative to an aldehyde. And we're going to look at a combination of two factors in this comparison. The first factor is the electronics. Electronic effects, the aldehyde is going to have a larger partial positive than the ketone, and that's because the ketone has two electron donating alkyl groups. And these electron donating alkyl groups help to stabilize the electron density that is removed from the carbonyl carbon via the resonance and induction. And then the second effect that's going to affect the electrophilicity of these carbonyl compounds is the sterics. The ketone has two carbonyl groups or carbon groups flanking it, where the aldehyde has just a small hydrogen next door. So the aldehyde is going to be more sterically accessible than the ketone. In order for a reaction to occur, different nucleophiles are going to require different conditions to be able to react with the electrophilic carbonyl group. Some will require acidic conditions and others will require basic conditions. In general, a strong nucleophile is going to be able to undergo nucleophilic attack in basic conditions, and this is because we won't need to activate the carbonyl group at all. A weaker nucleophile, however, will require acidic conditions because the protonation of the oxygen of the carbonyl group will increase the electrophilicity of the carbonyl carbon. The example that you've already seen in basic conditions is the Grignard reagent. The general mechanism in basic conditions will more or less look this way for all nucleophiles. Our first step is going to be nucleophilic attack, and once nucleophilic attack occurs, the electron density of the carbon-oxygen pi bond will move up onto the oxygen and create a negative charged intermediate on the oxygen. And then we can undergo an acidic workup or quench this with some sort of proton source, and that will result in an alcohol as the product, with the nucleophile also attached to the same carbon as the alcohol. And so this is the general mechanism that we can expect for our carbonyl compounds to undergo in basic conditions. In acidic conditions, we're going to have a different mechanism, and in acidic conditions, we're going to be able to obtain products where we use a weak nucleophile. The first step of the reaction in acidic conditions will be a proton transfer step where the oxygen of the carbonyl group is protonated, and this is going to make the carbonyl carbon even more electrophilic. So a weak nucleophile will then be able to attack, which will result in the product, which is also an alcohol attached to the same carbon as the nucleophile. If we look at the resonance structure of the intermediate after protonation occurs, we can see that we have an even more powerful electrophile than just a normal ketone, because in this resonance structure we can form a fully positive charge on the carbon, and there's no longer a negative charge on that oxygen. So protonation of the ketone is going to make it an even better electrophile. It's important for us to note, though, that these reactions, at least in the acidic condition, are going to all be equilibrium reactions. So when the nucleophile attacks the carbonyl group, the equilibrium, or which direction the equilibrium is favored, is going to depend on how nucleophilic the nucleophile is and how strong a leaving group will exist from the nucleophile. In this example, our nucleophile is also a good leaving group. So this will push the equilibrium towards the starting ketone, since the chlorine is going to be a better leaving group than most nucleophiles would be. Throughout this chapter, we're going to look at a large variety of nucleophiles and their reactions with ketones and aldehydes. We've categorized these nucleophiles into 5 sections: oxygen-containing nucleophiles, sulfur, nitrogen, hydrogen, and carbon-containing nucleophiles. And so we'll be forming new carbon-oxygen bonds, new carbon-sulfur bonds, new carbon-nitrogen bonds, carbon-hydrogen bonds, and finally, and one of the most important for building carbon-carbon building blocks, building larger and larger carbon frameworks, is carbon-carbon bonds. And we've actually already looked at 2 of these with the Grignard reagent and the nucleophilicity of cyanide, but we will learn about 1 additional carbon nucleophile. The first category of nucleophiles that we will look at are oxygen nucleophiles. In the presence of water, a ketone or aldehyde is at equilibrium with its hydrate. So this will just be the nucleophilic addition of water across the carbonyl. Unless we have acidic or basic conditions, the rate of the reaction is going to be extremely slow, and equilibrium will generally not be in favor of the formation of the hydrate. But let's look at the mechanism of this reaction. In the base catalyzed version of the reaction, and I just want to go back and say that this reaction is just going to set the stage for all of the carbonyl chemistry we're going to look at, where we form this tetrahedral intermediate, sp3 hybridized carbon intermediate. And so this mechanism is extremely important, both the base catalyzed hydration and the acid catalyzed hydration. We're also going to look at some tricks to get this reaction to push in the forward direction. So the carbonyl group is going to be in base catalyzed hydration, where we have an OH-. The carbonyl group is going to be attacked by the hydroxide, and that will form this anionic intermediate. So the first step, nucleophilic attack, and then a proton transfer will liberate our hydrate. So in basic conditions, we can form this hydrate. In acidic conditions, the first step will be a proton transfer. And so always in acidic conditions, the first step, proton transfer. Once we've obtained the protonated ketone or aldehyde, the second step will then be nucleophilic attack, which will be followed up by a proton transfer that will give the hydrate. So one thing that's important to note is that if we're dealing with a basic set of conditions, we will never have a positive charge in the mechanism. If we're dealing with an acidic set of conditions, we will never have a negative charge in that environment. So under acidic conditions, the mechanism will only be reasonable if it avoids the formation of or use of strong base. And the same holds true in basic conditions. So we've discussed in the past that alcohols are weak nucleophiles. So we can take a ketone or aldehyde, and in the presence of an alcohol, form an acetal. An acetal is similar to the hydrate we formed earlier, but in this case, we will be forming it with alcohols. So the acetal will have 2 ether linkages in it. For this to work, we're going to need to increase the reactivity of our carbonyl compound. We're going to increase the electrophilicity of it by using an acid catalyst. And here are a couple common acid catalysts that will be used for this reaction: toluene sulfonic acid and sulfuric acid. We can look at the mechanism of this reaction. The first step of the reaction, like any reaction with a carbonyl compound in acidic conditions, will be proton transfer. So the carbonyl group will be protonated to make the carbonyl carbon more electrophilic. Then the second step will be nucleophilic attack of the alcohol. So the oxygen with the lone pair on it will attack and form a new carbon-oxygen bond. Then a hemiacetal can form after deprotonation of this intermediate. So the hemiacetal is intermediate that's similar to the hydrate, where we have an OH on one side and an OR on the other side. Once a second proton transfer occurs, we can have water leave as a leaving group and reform our ketone. Then a second molecule of the alcohol can undergo a nucleophilic attack, and a proton transfer will finally liberate our acetal. So we can go from the ketone to the hemiacetal after one series of proton transfer, nucleophilic attack, and proton transfer. And then the hemiacetal is converted to the acetal after another sequence of proton transfer, loss of the leaving group, nucleophilic attack, and proton transfer. The formation of both the hydrate and the acetal is always going to be an equilibrium process. And so depending on the reagents that we use, we'll have a different result in this equilibrium. For simple aldehydes, the acetal is favored in the equilibrium. Remember, the aldehydes are more reactive than ketones. For most ketones, the acetal is not favored at equilibrium. The reactant of the ketone will be favored at equilibrium. We can also use a diol as a nucleophile. So if we use a diol as a nucleophile, we're going to obtain a cyclic acetal. The second nucleophilic attack stage will occur from the oxygen that's already very close to the carbonyl center that will form. So in the case of a diol, we will be forming a cyclic acetal. This is actually an extremely important reaction because the use of a diol in this reaction will help us to prepare what can be considered a ketone protecting group. So we can use the acetal formation reaction, and to convert the ketone into this acetal, if we add excess water and acid, we can convert the acetal back to the ketone. So if you remember when we were doing the Grignard reactions in the past, we used protecting groups on our alcohols. Well, we can also use protecting groups on ketones, and this is how we can protect it through the acetal. So if we take a look at this synthesis, let's say we would like to reduce an ester down to an alcohol, but not touch the ketone. Envision how we could do this. If we use LAH, it would reduce both compounds. So our solution will be to use a protecting group to first protect the ketone, and then we will reduce the ester. So the first reaction, we're going to use our diol and acid, and that will protect the ketone as an acetal. And then we can reduce the ester using lithium aluminum hydride. And then finally, we can remove the protecting group with acid to give back our ketone. If you recall, a hemiacetal was the intermediate that was formed in the conversion of a ketone or aldehyde to an acetal. In general, these will be difficult to isolate because the equilibrium will either form the acetal or the ketone will be favored in the equilibrium. But there are some cases where we can form and isolate a cyclic hemiacetal. For example, if we have a compound that contains both the carbonyl group and the hydroxyl group, then this cyclic hemiacetal will be favored at equilibrium because this is an intramolecular reaction. The alcohol from one reactant is already very close to the carbonyl group. It's already kind of locked in position there, since the fact that it's already part of the molecule brings it closer in proximity. And these are important in carbohydrate chemistry. Most sugars are made from the cyclic hemiacetals of For example, here's glucose in its linear form, and then at equilibrium, it's actually favored in this six-membered ring cyclic hemiacetal.